Welcome to the Explainer, everyone. You know, whenever we hear about the health of our oceans, the conversation almost always circles right back to the usual suspects, right? We're talking rising temperatures, nutrient runoff, coral disease. And yeah, absolutely, those are massive pieces of the puzzle. But today, we're actually going to set those aside for a minute. We're zooming right past that macro level and diving straight into the microscopic chemistry of a coral reef. We're going to look at this invisible molecular world that literally shapes the foundation of these incredible ecosystems. Okay, let's dive into this. Have you ever stopped to think about what actually builds a coral reef? I mean, physically, literally builds it. Because when we look at those massive, sprawling underwater structures spanning miles of ocean floor, what are the actual molecular ingredients required to construct them? Corals aren't just sitting there. They are actively building. And to build, well, you need raw materials. Think of corals as the ultimate underwater architects. They don't just find rocks and stack them up. They actually pull invisible, dissolved seawater chemistry straight out of the current and transform it into a rigid physical structure. Specifically, they're producing a mineral called calcium carbonate. And a lot of reef-building corals prefer a highly specific crystal form of this called aragonite. Basically, this is the concrete of the reef, and just like pouring concrete, the chemical conditions have to be exactly right for it to set properly.
Here is our roadmap for today. 1. The coral construction site. 2. Calcium, the building blocks. 3. Alkalinity, the supply line. 4. Magnesium, the mineral modulator. 5. The chemical triangle. And finally, 6. The future of reefs.
Section 1. The coral construction site.
Imagine a growing reef not just as a habitat, but as a bustling 24/7 construction zone. And here is the roster for our big 3 molecular ingredients needed on site: calcium, alkalinity, and magnesium. Together, these 3 dictate the underlying stability of calcification. If this specific chemistry shifts, it's like the supply trucks just stop. Growth slows down, and the skeletons become weak and brittle.
Section 2. Calcium, the building blocks. So if the reef is a construction site, calcium is essentially your truckload of bricks. But here's the really surprising part. Calcium is actually relatively abundant in the ocean. It rarely just runs out. So when corals fail to grow, it's usually not a lack of calcium bricks. Instead, other environmental stressors reduce their calcification efficiency, which means they produce way less material even when the calcium is sitting right there for the taking.
Section 3. Alkalinity, the supply line.
Now, what's really interesting about this slide is the stark contrast. If calcium provides the bricks, alkalinity is what ensures the mortar actually arrives on site. On the left, we've got normal buffering, a high capacity to neutralize acids, plenty of carbonate ions, and super robust reef building. But on the right, that's the catastrophic reality of ocean acidification. Lower pH effectively ties up all those carbonate ions. And frankly, it doesn't matter if you have all the calcium in the world. If acidification cuts off that carbonate supply line, calcification becomes incredibly hard for the coral. It leads to slower growth and much thinner skeletons.
Section 4. Magnesium, the mineral modulator. So magnesium is present in seawater in really high concentrations, but researchers describe its role uniquely. They call it a modulator. If calcium is the brick and carbonate is the mortar, magnesium is the meticulous site manager overseeing the whole operation. It heavily influences exactly how the structure is built without actually becoming the main piece of it.
Let's look at exactly how this site manager operates. Step 1, it influences the crystal formation pathways. 2, it dictates how those aragonite crystals arrange themselves. And 3, it determines the ultimate characteristics and stability of the skeleton. And, sudden shifts driven by ocean upwelling or water mixing make this site manager's job exponentially harder.
Section 5. The chemical triangle. Let's move to and see how this builds into an interconnected system.
Because out in the wild ocean, these ingredients don't work in isolation. They are completely dependent on one another. Coral calcification is this totally interconnected, multi-ingredient reaction. We've got slice 1, calcium availability. Slice 2, alkalinity-driven carbonate chemistry. And slice 3, magnesium's mineral modulation. If even one part of this triangle collapses, like, say, acidification shrinks that carbonate slice, the entire structural resilience of the reef is completely threatened. It's a real house of cards.
Section 6. The future of reefs.
Understanding this chemical triangle really explains why, under the exact same global climate pressures, some reefs survive while others completely fail. Local water chemistry conditions act as either a buffer or a dangerous accelerant. Factors like watershed runoff, local pollution, upwelling, and warming-driven stratification can drastically alter how seawater interacts with carbon dioxide. These local factors can either cushion the corals against chemical stress or, unfortunately, accelerate their decline.
And that brings us to a highly practical takeaway. As researchers in coastal communities intensify their coral restoration efforts, this underlying chemistry absolutely cannot be ignored. Monitoring alkalinity, pH, and magnesium is crucial for predicting reef health. In fact, maintaining or restoring favorable conditions, especially regarding that carbonate availability, might be just as vital as ensuring corals have suitable light and reducing physical stress. Think about it. You can't just plant a coral fragment, walk away, and hope for the best. You have to ensure the construction site actually has its supply lines open.
Which leaves us with this final really important thought to ponder. As global climate pressures continue to intensify, we know for a fact the ocean is changing. But knowing that the literal survival of these coral architects depends on this microscopic balance of calcium, alkalinity, and magnesium, how will we manage our local coastal waters to maintain that delicate chemical balance? Because if we truly want to save our reefs, we have to start by protecting the invisible chemistry that actually builds them. Thank you so much for joining me on this explainer today. Keep asking those big questions, and I'll catch you next time.